ngayong araw, i-explain natin kung ano nga ba ang recursion sa Python programming. Siyempre, magpapakita tayo ng mga example kung paano nga ba ito nagana at ang ilan sa mga pros and cons nito. Magsimula agad tayo sa isang example. Find 5 factorial. Kung di nyo alam kung ano ang factorial, pinapakita ito gamit ang kahit anong positive number na may kasamang exclamation point. Nasasagot ito sa pamamagitan ng pagmultiply ng lahat ng number mula sa napiling number hanggang sa 1 at maliban sa 0. So bale, 5 times 4 times 3 times 2 times 1 is equal to 120. May ilang rules ang factorial, na ang factorial ng 1 at 0 ay palaging equal sa 1. So ngayon naman, gumawa tayo ng algorithm na sasagot sa factorial ng kahit anong number. Ang isa sa algorithm para masagot ang ganitong problem ay ang iterative algorithm. Ang ibig sabihin ay gagamit tayo ng loop upang maulit ang computation ng factorial hanggang sa napili nating number. Ang isa namang way para magawa ito ay gamit ang recursion. At sa programming, gagamit tayo ng recursive function. Ang ginagawa ng recursive function ay hinahati nito ang ating problem sa maliliit pa na mga problem. At kung gagamitin natin ito para masolve ang ating problem, ang mangyayari ay kukuhanin nito ang factorial ng 5. At kung mapapansin nyo, kailangan naman natin i-multiply ang factorial ng 4 habang ina-execute ang function. So, uulitin natin ang pag-execute ng function sa loob nito para naman solve ng function ng factorial ng 4. At bago matapos yun ay factorial naman ng 3 hanggang sa makarating ito sa 1. At pagtapos nito, muli nito ibabalik ang mga nakuhang value mula sa 1 pabalik naman sa 5. So, ganito ang mangyayari sa ating algorithm. Kung gagawa tayo ng function na may pangalang getFactorial na may value na 5, magre-return ito ng sagot na 5 times getFactorial na may value naman ng 4. So ngayon naman, tatawagin ulit natin ang getFactorial function na may value na 4 at magre-return ito ng getFactorial na may panibagong mas mababang value hanggang sa makarating ito sa ating base case na factorial of 1 is equal to 1. Pagkatapos ng mga ito ay muli itong babalik pataas kasama ng mga exact value na nakuha nila sa mga recursive functions hanggang sa ating unang function na getFactorial na may value na 5. So ito naman ngayon ang pros and cons ng recursion. Habang nangyayari ang isang recursion, walang calculation ang nasisimulan hanggat di nararating ng recursive functions ang ating base cases. So kung tayo ay magsosolve ng mga malalaking values, malaki ang chance na maubusan ng memory ang ating ginagamit na PC or any console sa kadahilan ng napakaraming functions ang naka-open na di maaaring bitawan ng ating memory. So, sa sunod naman nating cons, kung ikukumpara natin ang recursion at iteration, di gaya ng iteration, ang recursion ay mabilis at malakas kumuha ng memory dahil sa pagbubukas ng maraming functions. Sa pangatlo naman nating cons, may mga programming language na mas mabilis sa paggamit ng mga iteration kaysa sa recursion. Maaaring mas mabilis ito sa pag-execute ng mga loops, pero mabagal naman magbukas ng mga functions. Ngunit kung Python 3 ang inyong gagamitin, base sa aking experience, mas mabilis ang Python 3 sa pagbubukas ng functions kaysa sa paggamit nito ng mga loops. Para naman sa ating pros, once na nakagawa na tayo ng isang maayos na recursive function, mas mababa ang chance nito na magkaroon ng bugs at errors over time. At ang isa pa sa pros ng recursions ay may mga cases na mas madali itong i-code at nagiging sobrang bilis nito, lalo na sa mga program na may tree traversals at binary searches.
Introduction. When an algorithm involves an iterative control construct, such as while loop or for loop, its running time can be represented as the amount of the time spent on each loop's execution of the body. The summation or series can be obtained by adding up the time spent on each iteration. Given a sequence of a sub 1, a sub 2 of numbers, the finite sum of a sub 1 plus a sub 2 plus a sub n, where n is a non-negative integer, can be written. If n is equals to 0, the value of this summation is defined to be 0. The value of a finite series is always precise and distinct, such that its terms can be added in any order. Given a sequence a sub 1, a sub 2, a sub 3, a sub 4, a sub 5 of numbers, the infinite sum of a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5 plus a sub n can be written. On the other hand, when an algorithm has a recursive call to itself, its running time can often be described by a recurrence. A recurrence is an equation or inequality that describes a function in terms of its value on smaller inputs. There are three methods for solving recurrences, namely substitution method, recursion tree method, and master method for obtaining asymptotic or O-bounds of the solution. Substitution method. The substitution method for solving recurrences involves two steps. One is guessing the form of the solution, and two, using mathematical induction to find the constants and show that the solution works. The name substitution method originates from the substitution of the guessed answer for the function when the inductive hypothesis is applied to smaller values. This method can be used to set either upper or lower limits on a recurrences. Given as the example, find an upper bound of the recurrences. T of n is equals to 2t of n divided by 2 plus n. Remembering the first step, guess that the solution is t of n is equals to 0 or of n lgn. The method is to verify that t of n is greater than c of n lgn. For an appropriate choice of the constant, c must be greater than 0, starting by assuming that this bound or limit holds for n divided by 2. That t of n divided 2 is less than or equal to c of n divided 2 lg n divided 2. Substituting into the recurrence will result to the last step holds as long as c is greater than 1. For the second step, mathematical induction now requires to demonstrate that the solution is in line with the boundary or limiting conditions. The demonstration must allow to choose the constant c large enough so that the bound or limit where t of n is less than or equal to c of n lgn works for the boundary conditions as well, although sometimes this condition can result to problems. Assume that t of 1 is equals to 1 is the sole boundary condition of the recurrence. The boundary t of n is less than or equal to c of n lgn, with the value of n is equals to 1, shows t of n is less than or equal to c of 1 lg of 1 is equals to 0, which does not satisfy t sub 1 is equals to 1. T of 1 is equals to 1. Consequently, the base case of the inductive proof fails to hold. But this difficulty in proving an inductive hypothesis for a specific boundary condition can be overcome. For most of the recurrences, there shall be an analyzation whether it is straightforward to extend boundary conditions to make the inductive assumption work for small n.